Can laser sails reach Alpha Centauri in 20 years? Rockets chase fuel and pay an exponential tax for every extra meter per second. Light sails borrow momentum from photons and leave the heavy engine at home. The top 1% of propulsion concepts exploit this, and they don't look like rockets at all. There's a 400-year thread that runs from Kepler noticing comet tails to Caltech's microscopic trampolines that finally measure light's push directly. Miss the reflectivity by 0.01% and your sail vaporizes. Nail it and Alpha Centauri becomes a 20-year coast. Here's the promise. In this episode, you'll see how laser sails bypass the rocket equation, why reflection doubles the momentum transfer, how a wafer-thin membrane survives 1,000 plus G, and how a Gram-class probe whispers home across 4 light years. We'll also open a surprising door, a mission profile that flips from Interstellar to a 3-week Mars run, plus the vaporization limit that makes or breaks the whole idea. Let's start where the loophole opened. Kepler to Maxwell, the reality loophole opens. Kepler wasn't thinking about starships. In 1610, he was thinking about comets, and he noticed something almost mundane. Their tails always pointed away from the sun. Not sometimes, always. The thing most people miss is what he inferred from that geometry. He guessed that sunlight itself was exerting a pressure, pushing dust and gas outward. No engines, no propellant, just light doing work. Why does that matter? Because if light carries momentum, then in principle you can trade mirrors for fuel. The benefit is obvious. If you don't carry propellant, you don't pay the mass spiral that kills rocket performance. The consequence of ignoring it is you keep brute-forcing missions with bigger tanks and get diminishing returns. This clicked for me when I first learned the follow-up. James Clerk Maxwell's equations in the 1860s. Maxwell didn't just unify electricity and magnetism. His math shows electromagnetic waves carry momentum. The reason this works is simple conservation. A photon striking a surface transfers momentum. A photon reflecting transfers roughly twice as much because it reverses direction. That reflection doubles it. Idea is the shortcut nobody teaches in intro texts, but it's critical for sails. Now you might be thinking, if this is real, why didn't we sail centuries ago? Because the pressure is tiny. Sunlight at Earth gives you a few micropascals. Picture the weight of a mosquito spread over a square meter. Early 1900s lab work by P.N. Lebedev in Russia and Ernest Nichols and Gordon Hull in the U.S. used torsion balances to prove the force exists, but the numbers screamed impractical for anything fast. The game changed when 2 things arrived: coherent light and ultra-thin materials. Before we continue, you need to understand persistence. Rockets deliver huge thrust for minutes, then coast forever. Light pressure looks useless at first because it's weak, but it never runs out as long as you're in the beam. With sunlight, that persistence turns into gradual velocity compounding. Tsiolkovsky-era and later sailing advocates leaned on this, tiny pushes adding up over weeks and months. But here's where most people mess up. They hear sunlight sails and conclude all sails are slow. That's like tasting rain and claiming hurricanes can't exist. Sunlight is a drizzle. Lasers are engineered storms. Concentrate power by orders of magnitude. Keep the mass microscopic, and suddenly micropascals become kilopascals at the sail, and accelerations jump from millig's to thousands of G's for grams. Let me show you exactly how the mental model shifts. Why rockets are penalized by the rocket equation. Adding fuel to go faster makes you heavier, which needs more fuel. What? Use externalized energy, beam power delivered from a phased laser array, to push a reflective sail. How? Maximize reflectivity to double momentum transfer, minimize mass per unit area, and keep the beam tight long enough to build speed. The result is a regime where a 3-minute push sets your final cruise velocity for decades. The early experiments did more than confirm a textbook prediction. They set the measurement mindset we still need. When forces are micro to piconewtons, your instruments must see picometer motion and isolate thermal effects from real pressure. That's why today's lab sails double as sensors, resonant structures where light, pressure, and heat leave distinct fingerprints. We'll get to Caltech's version in a moment, but note the through line. Observe a subtle force, model it rigorously, then build hardware that can measure and survive it. Common mistake: thinking the small magnitude of solar radiation pressure at 1 AU implies an absolute ceiling on sail performance. The limiting factors are intensity at the sail, reflectivity, and beam control, variables you can engineer. Once you nail that, everything else clicks. A perfectly reflecting surface not only doubles the push, but also minimizes absorption, which keeps the sail from cooking under a multi-gigawatt spotlight. Here's the shortcut nobody teaches in popular explainers. Reflectivity is both your thrust multiplier and your thermal life insurance. Absorb parts per million and you live. Absorb fractions of a percent at gigawatt power densities and you die in microseconds. That dual role sets the stakes for materials, which is why the story soon moves from equations to nanofabrication. Microstory. A student in a lab measures a membrane's vibration when they sweep a laser across it. It's barely there, picometers, but the pattern tells you where momentum transfer is pure radiation pressure and where it's thermal creep. Once they separated those signals, the design iteration sped up. The difference? They finally understood that optical design and mechanical resonance are inseparable at this scale. Set this as a checkpoint. If you remember nothing else, remember that reflection doubles momentum transfer, and persistence makes weak forces powerful. Those two principles justify everything that follows. Why phased arrays matter, why metamaterials matter, and why gram-scale payloads suddenly make sense. Now, transition to the inflection point. Sunlight proved the physics but not the performance. Lasers concentrate intensity. Nanoscale sails minimize mass. Interferometry validates forces at the threshold of measurability. The reality loophole that Kepler spotted becomes an engineering path when you can build, measure, and iterate on devices thinner than a fraction of a wavelength. Next up, the microscopic trampolines that let us see the push and set the bar for materials that won't melt when the storm hits. The rocket equation, tyranny versus externalized energy. Okay, so we've opened the loophole, photons push. Now let's confront the wall rockets hit every time, the rocket equation. Before we continue, you need to understand why bigger tanks don't fix slow missions. The thing most people miss is that rockets pay twice for fuel. You carry it, and then you carry the extra structure to hold it, and then you carry more fuel to push that structure. It's exponential pain disguised as engineering bravado. Here's the short version. The Tsiolkovsky rocket equation links your change in velocity to the ratio of starting mass to ending mass and your exhaust velocity. You want more delta V. Either increase exhaust velocity, which is hard, or accept a mass ratio that balloons fast. That's why deep space missions stack gravity assists like coupons. They're dodging the brutal math. Add a little more speed, and the propellant fraction dominates everything. Now you might be thinking, can't we just use nuclear engines? Higher exhaust velocity helps, but the curve still bites. You're still carrying the energy and the reaction mass. That's the trap. The game changer nobody talks about is to divorce the spacecraft from its energy source. Externalize the energy. Keep the engine on Earth. The reason this works is you eliminate carried propellant. A light sail doesn't throw mass. It intercepts momentum from a beam you control from the ground. That instantly flips the scaling. Instead of delta V costs exponential mass, you get acceleration is proportional to power divided by mass and area. Put simply, for a given power on the sail, cut mass, and you climb into absurd acceleration regimes. Reflectivity multiplies that because a reflected photon gives roughly twice the momentum kick of an absorbed one, while dumping far less heat. Let me show you exactly how the new scaling feels. What matters is power on target, spot size, reflectivity, and total mass. Acceleration scales like power times reflectivity divided by c times mass, with geometry baked in. Double the power or halve the mass and you double acceleration. No propellant penalty shows up later to tax you. That's why Graham-class payloads make sense. They live where the ratio is ridiculous. Now here's where most people mess up. They equate fast with short, violent burns. For rocket thinking, sure. But with beam propulsion, long thrust arcs beat impulsive burns because you can keep adding velocity as long as you hold beam control. Sunlight gives you millig's for months. Lasers let you compress that into minutes or hours at thousands of Gs for gram scale craft, or tens of millig's to Gs for kilogram class probes. Same physics, different knobs. This clicked for me when I ran the persistence thought experiment. With a beam you control, thrust is on demand. You don't pay to lift fuel only to discard it. You turn the engine on, the craft accelerates. Turn it off, it coasts at that speed for decades. The reason this changes the mission design is you concentrate cost on a reusable ground engine instead of expending hardware with every launch. Let's address the belief break. Faster pacing isn't the fix by itself. You need sustained, guided thrust to accumulate meaningful delta V without hauling propellant. That means diffraction-limited beam forming, adaptive optics to punch through the atmosphere, and a sail that reflects almost everything. The sail's optical properties become your throttle. Higher reflectivity gives more thrust per watt and less heating per watt. Miss that by 0.01% at multi-gigawatt flux, and you cook the sail. Nail it and you sprint. Common mistake, assuming acceleration is free with a beamer. It's not. You pay in power and aperture. Beam divergence sets how long you can stay on the sail before the spot grows too large. Therefore, the scaling law is really a triangle: power, aperture, and mass. Increase aperture, hold the spot tight longer and you push farther. Increase power and the early acceleration spikes. Reduce mass and everything gets easier. The reason this trio matters is it replaces the old mass ratio obsession with an optics and power optimization. Micro story. A team modeled two mission profiles for the same laser. In the first, they oversped a Graham craft to 0.2 C in minutes. In the second, they throttled down and held beam lock longer on a 20-kilogram probe, trading peak G load for a weeks-long thrust arc that cut a Mars transfer from months to weeks. Same engine, different use case: interstellar or rapid solar system logistics. If you remember nothing else from this section, remember this. The rocket equation punishes you for carrying energy and reaction mass. Externalized energy pays you for leaving both at home. That's the mental flip. Open loop planted. All of this hinges on a material paradox. To exploit externalized energy, the sail must be feather light, almost perfectly reflective and robust under brutal flux. That combination decides whether you accelerate or vaporize. And before the furnace test, we need proof that light pressure can be measured, separated from heating, and used to guide stability. That's why we're about to shrink from kilometer arrays to Caltech's microscopic trampolines. The lab bench where we learned how to measure the push, tune the optical response, and build a sail that won't shred when the power comes up. Caltech's microscopic trampolines, measuring the unmeasurable. We've talked about principles. Now let's shrink to the bench where those principles get punched in the face by reality. At Caltech's Kavli Nanoscience Institute, the microscopic trampoline is both a prototype sail and a force sensor. It's a square of silicon nitride about 40 microns across, roughly the width of a fine human hair, and just 50 nanometers thick, 1/1000th the thickness of that hair. It's tethered at its corners by tiny springs of the same material. That suspension turns it into a resonator that moves in clean, measurable modes when light hits it. Why bother with a trampoline? Because when radiation pressure and heating act together, they produce motion that looks similar at first glance. If you can't separate those fingerprints, you'll design the wrong sail. The thing most people miss is that pressure acts instantly with the beam, while thermal effects lag and drift because heat diffuses and bends the structure differently. This is where interferometry becomes the microscope for motion. Split a reference beam, reflect it off the membrane, recombine the paths, and watch the interference fringes shift by picometers, smaller than an atom's diameter. Those shifts map to displacement and rotation in real time. Here's the shortcut nobody teaches. Make your prototype do double duty. The Caltech membrane is both the sail and the instrument. Hit it with an argon laser, record the up-down, side-to-side, and twist modes, then vary wavelength, power, and angle to tease apart momentum transfer from photothermal creep. Rotate the beam off-center, and you inject a clean torque, which lets you read out photonic angular momentum coupling and alignment sensitivity, the same knob you'll use later for orientation control in flight. Now the tricky part. Heat wants to ruin your data. Even parts per million absorption in ultra-thin films will cause measurable bending as temperature gradients develop across the square. Actually, let me back up and explain this better. Silicon nitride has excellent tensile strength and low mass density, but its optical absorption and thermal conductivity still matter at these scales. So the team runs in high vacuum to kill convection, stabilizes ambient temperature, and calibrates stiffness of the springs. They also do power sweeps and frequency sweeps. Power sweeps expose the membrane to different intensities. Frequency sweeps look for resonance where tiny pushes produce big motions. If the signal spikes at a mechanical mode and scales linearly with power without thermal lag, that's your radiation pressure signature. Once you nail that, everything else clicks. You get a force constant, piconewtons per watt, validated by direct measurement. That number becomes the anchor for your optical design models. You can now change the surface micro pattern, add a meta-grading, a subwavelength lattice, or a diffractive motif, and immediately see how momentum flows into translation versus torque. The reason this works is that a patterned surface redistributes diffracted orders, and with careful asymmetry you can build passive beam riding stability. Drift left, the local optical field kicks you right. Drift right, it kicks you left. No fuel, just light steering light. Common mistake, building over rigid prototype. Stiff feels safe, but it amplifies resonance if the drive couples near a mode. Better is high tensile stress for flatness, paired with damping pathways so energy doesn't ring. Calibrated perforations and spoke-like lattices spread stress and increase emissivity without wrecking reflectivity. And yes, perforations can improve thermal handling by breaking up hot spots while barely touching mass per area. What about absolute numbers? In this regime, forces are piconewtons to tens of piconewtons for modest lab powers, and displacements are tens to hundreds of picometers on resonance. That sounds tiny until you remember the mission scaling. Swap a 40-micron square for a meter-class sail and an argon bench laser for a phased array with gigawatts, and the dimensionless coefficients, the transfer functions, carry over. The lab's job is not to brute force thrust. It's to validate the math that tells you what happens when power goes up a billion-fold. Let me show you exactly how the validation loop runs. Step 1. Simulate the optical field and mechanical modes for a candidate pattern on a thin silicon nitride membrane. Step 2. Fabricate with electron beam lithography and release the membrane from the wafer. Step 3. Measure with interferometry while sweeping beam angle and power, logging linear and rotational responses. Step 4. Compare phase and amplitude with the model. Step 5. Iterate geometry to boost reflective efficiency, suppress parasitic absorption, and tune beam riding stability. Each loop shaves uncertainty on reflectivity, on stiffness, on thermal time constants. Micro story. A researcher noticed a shallow drift in the rotation channel minutes after a power step. At first it looked like noise. Then they realized it was a thermal gradient bending the corners asymmetrically. They tweaked the anchor geometry and added a sparse perforation grid. The drift vanished, the torque response sharpened, and the next set matched the model within a few percent. The difference was understanding that flat is not just geometry, it's thermal behavior under load. If you remember nothing else here, remember this. Measurement is propulsion. Without picometer readouts, you can't separate push from heat or stability from luck. The trampoline turns invisible forces into numbers you can design against. Open loop for what's next. The lab proves we can see and shape the push. But scaling that push demands sitting under a multi-gigawatt spotlight without melting or tearing while taking thousands of Gs. The material must be almost perfectly reflective, feather light, and thermally honest. Up next, the vaporization limit. The furnace test every sail must pass before it ever meets the beam. The vaporization limit, material science at the edge. This is the furnace test. The sail has to do three contradictory things at once: reflect almost every photon, weigh almost nothing, and shrug off brutal power density without warping or tearing. Miss any corner of that triangle and you either crawl or you vaporize. Why it matters: thrust and survival are the same knob. The thing most people miss is that reflectivity doesn't just give you more push, it keeps you cool. Absorbed power turns into heat. Under multi-gigawatt illumination, a fraction of a percent absorption is lethal. At parts per million, you live. At tenths of a percent, you're gone in microseconds. The real-world impact is simple. Reflectivity and emissivity become propulsion parameters. What do we build with? Today's front-runners are crystalline or high-stress silicon nitride, synthetic diamond films, and engineered metasurfaces that steer light with nanoscale patterns. Silicon nitride earns its spot because it stays strong at tens of nanometers, holds tensile stress for flatness, and can be patterned wafer scale. Diamond brings phenomenal thermal conductivity and stiffness at low mass, plus outstanding infrared transparency that helps radiate heat. Metasurfaces are the game changer nobody talks about enough. Subwavelength features that set how light is reflected, diffracted, and phased, so you can push while stabilizing, and you can route power away from hot spots. How do you make something this finicky? Atomic layer deposition and ultra-clean thin film growth for near-perfect layers. Electron beam lithography and nanoimprint for sub-100 nanometer features, and nanometer flatness over meter-class spans. Actually, let me back up and explain this better. A flat mirror at optical wavelengths means surface variations much smaller than the wavelength. If your beam is near a micron, your tolerances are single-digit nanometers. Otherwise, you create speckle, local intensity spikes, and absorption hot spots that kill you. Thermal management isn't an afterthought, it's the plan. In vacuum, you can't convect heat away, so you radiate. Emissivity at thermal wavelengths becomes your heat sink. The shortcut here is spectral separation. Make the sail highly reflective at the drive wavelength while highly emissive in the mid-infrared. Multi-layer stacks and photonic crystals can do that. Mirror where you need push, blackbody where you need to dump heat. Perforations help too. Done right, sparse micro-perfs reduce mass, increase radiative area, and relieve thermal stress without wrecking optical efficiency. The common mistake is random perforation that scatters the drive beam and seeds instabilities. Pattern has to be intentional, aligned with the optical field so diffracted orders stay controlled. Structurally, tensile lattices spread load and resist tearing under thousands of Gs. Think spokes and rings that carry stress without adding thickness. Mode shapes matter because high-Q resonance plus pulsed or noisy beam power is a recipe for catastrophic growth. That's why damping paths, graded stiffness, and anti-node placement are baked into the layout. Once you nail the mechanical spectrum, everything else clicks. You can predict how the sail deforms with heat and how it responds to torque for alignment. Let me show you exactly how the absorption math bites. Say the beam delivers tens of megawatts per square meter. At 0.1% absorption, that's tens of kilowatts per square meter of heating on a film thinner than a red blood cell with no convection. Temperature soars, the film bows, reflectivity drops locally, absorption rises, and you get a runaway. At parts per million absorption, the same scenario drops to watts per square meter. Now radiative cooling with emissivity-tuned coatings can keep up. That's the vaporization limit in one picture. Manufacturing reality sets the floor. Nanometer-level roughness, pinholes, and contamination dominate absorption, so process control is propulsion. Ultra-high vacuum deposition, in situ metrology, and post-fabrication annealing all attack defect density. Even tiny grain boundaries or inclusions can seed hot spots. The industry lesson applies. If you can't measure it, you can't ship it. That's why lab sales start as metrology specimens, ellipsometry for optical constants, AFM for roughness, IR thermography for emissivity maps. Metasurfaces add a second lever. You can route momentum with phase gradients. One-dimensional subwavelength gratings, for example, can reflect most power into a controlled order while creating passive beam riding stability. Drift left, local phase tilts you back. Drift right, it corrects the other way. The reason this works is you're shaping the scattering matrix so lateral error produces restoring torque. The payoff is huge. Less active control, less heat, and better survival odds under uneven illumination. Micro story. A prototype stack looked perfect on spec sheets but failed under power. Post-mortem showed nanoscale residues from a lift-off step acting like tiny absorbers. A switch to a fully subtractive patterning flow, plus an oxygen plasma clean, cut absorption tails dramatically. The next run held reflectivity above 99.95% at the drive band and radiated heat efficiently in the mid-earth. Same base material, different process discipline. That was the difference between scorched in milliseconds and stable under load. Limits and trade-offs. Diamond is amazing but expensive and tricky to grow large and flawless. Silicon nitride is scalable but needs careful spectral design to hit both reflectivity and emissivity targets. Metasurfaces boost control but add fabrication complexity and potential scattering loss if features are off by even a few nanometers. Distinguish best practice from preference. For early DMOS, high-stress silicon nitride with simple gratings may win on manufacturability. For later high-flux missions, diamond-based stacks with multi-band photonic layers could dominate. If you remember nothing else, remember this. Reflectivity is thrust and cooling. Emissivity is survival. Process control is propulsion. Get those right, and the sail lives in the storm. Up next, we've solved heat on paper, but the beam still slams the structure with thousands of Gs. How does a membrane thinner than a soap bubble survive the G-force paradox that would shred? How a sail survives thousands of Gs. We've solved heat on paper, but there's a second cliff: acceleration. A Graham-class probe can see thousands of Gs during a minute's-long push. The thing most people miss is that G-load isn't a single number smashing everything equally. It's how that load distributes through geometry, tension, and mode shapes. If you spread force in pure membrane tension, a film that would crumple in bending suddenly behaves like steel cable. Why this matters? At 1,000 plus G, local stress concentrations, not the average load, kill you. A sharp corner, a stitched line, a thickness step becomes a stress razor. The benefit of mastering this is you trade catastrophic failure for predictable deformation you can design around. The consequence of skipping it is a tear that races across the sheet faster than you can blink. What does a survivable acceleration profile look like? Think ramp, not hammer. You shape beam power to rise below any structural resonance, hold a plateau, then taper. That avoids pumping energy into vibrational modes. The sail carries most load and tension. The payload sits at the geometric center where strain is lowest. Spoke and ring lattices keep the film flat and transmit load radially. Spin stabilization adds a steady tension bias, like a drum skin under tunable torque. Here's the shortcut nobody teaches. Tune your mechanical spectrum before you ever see the laser. You map mode shapes, those standing wave patterns a membrane prefers, and you move antinodes away from sensitive areas. Antinodes are the big deflection zones where small forces become large motions. Place your lattice supports there, add damping paths, and you strangle growth. This is where perforations earn their keep again. They're not just for heat. Properly placed, they break up long, high-Q modes into shorter, lossy ones that die fast. Now, how do you actually damp something this light? You don't glue on mass. You control material loss and geometry. High-stress silicon nitride has low intrinsic damping, which is great for metrology and terrible for runaway resonance. So you introduce engineered loss tangents in sacrificial ribs, micro hinges, or viscoelastic edge anchors at scales that don't wreck reflectivity. Spin helps too. A slow spin turns random kicks into tiny, averaged misalignments while gyroscopic stiffness resists wobble. Once you nail that, everything else clicks. Beam structure matters as much as sail structure. Phasing errors create amplitude modulation, little beats that act like a mallet. You mitigate with beam smoothing, adaptive optics that suppress low-frequency wander, and control loops that refuse to excite known modes. The sail's optical pattern helps here. Diffractive metagratings can convert small lateral drift into restoring torque, which keeps the beam centered and reduces off-axis forcing that would wrinkle the sheet. Common mistake over rigid designs. Engineers see thousands of Gs and add stiffness everywhere. That moves resonant frequencies up, but closer to where beam control errors live and concentrates stress. Better is compliant in bending, strong in tension. Think of a slack line that becomes rock solid when pulled tight. Under illumination, thermal pre-tension rises. You design to harness that, not fight it. Let me show you exactly how orientation control lives inside the optics. Offset the payload slightly behind the sail. Now the beam's center of pressure sits ahead of the center of mass like a dart. Add asymmetric subwavelength gratings that throw a few % of light sideways when you drift. Drift left, you get a righting torque. Drift right, the pattern flips. No propellant, just photonic torque. If you want active control, you embed micro-reflectors that switch phase with tiny heaters or MEMS actuators, but the baseline should fly passive. Swarm redundancy changes the stakes. Instead of one heroic sail, you launch 100. Fault-tolerant lattices mean a tear in one panel doesn't doom the whole sheet. Load paths route around damage. If 5% of the fleet fails under acceleration, the mission still succeeds. That mindset pushes you to modular tiles you can fabricate, test, and stitch. A manufacturing win and a risk win. Micro story. A team saw a violent pitch oscillation at 600 Hz whenever the beam ramped fast. Slowing the ramp helped, but the cure was geometric. A narrow annulus near the rim was acting like a tuning fork. They widened the rim lattice, added a sparse perforation ring, and shifted the mode to 1.1 kHz out of the beam's noise band. The oscillation vanished, and alignment error dropped by an order of magnitude. The difference was recognizing that G-load arrives through modes, not magic. If you remember nothing else, remember this. Distribute load and tension, avoid exciting modes, and let light enforce alignment. The paradox isn't a paradox when the membrane is designed to live as a taut, actively stabilized optic. With a sail that survives the push, we can finally ask the fun question: where do we go first? Interstellar ambition versus local payoff. We've got a sail that can survive heat and G-loads. So the obvious dream is Starshot. 0.2 C in minutes, 20 years to Alpha Centauri, a few seconds of flyby science, and a whisper of data crawling back over 4 light years. That's the headline. But now here's where most people mess up. They jump straight to stars and skip the near-term win that actually funds and de-risks the whole program, turning the same engine toward our own backyard. Why this matters? Interstellar is a marathon of unknowns, decades of exposure, dust impacts, microwatt communications, no braking. The payoff is huge but delayed. The local payoff flips the equation. You use the same ground engine, the same sail physics, but you scale payloads up and velocities down. Suddenly, you accelerate 550 kilograms to tens of kilometers per second and transform solar system logistics. The result is faster missions, richer instruments, and repeatable cadence. What does that look like? Starshot macro first. You phase a massive array, punch through the atmosphere with adaptive optics, ramp power cleanly, and kick a gram-scale craft to 60,000 kilometers per second. It departs in minutes, coasts for 20 years, then streaks past Proxima's planets with milliseconds to react. Instruments must auto-trigger, compress, and transmit minimal data with brutal pointing constraints. You get a handful of images, spectra, and fields measurements if everything works. Now the pivot. Take the same array and run it in a different regime. You don't need thousands of Gs. You want sustained, moderate acceleration that a multi-kilogram probe can survive comfortably. You hold the beam longer by accepting a lower terminal speed, or you switch to a hybrid profile where you heat propellant in a laser thermal stage for initial impulse, then deploy a sail for continued push. The game changer nobody talks about is reuse. The ground engine resets between shots. Spacecraft become cheap. The engine is amortized. Economics first because it's the hidden lever. Rockets are single-use performance wrapped in expensive tanks. With a beamer, the costly hardware stays on Earth. Power draws coupled to the grid and storage. Maintenance is local. Upgrades are incremental. That means you can fly often. Mission cadence goes from 2 planetary flagships per decade to responsive launches against transient targets. A comet outbursts. You dispatch within days. A methane plume appears on Mars. You intercept in weeks. Once you nail cadence, everything else clicks. You design instrument suites knowing they'll fly again. You test autonomy on a lunar relay, then roll it to a Mars scout, then out to the outer planets. You standardize avionics across masses. A 5-kilogram probe for rapid meteorology, a 20-kilogram lander for plume sampling at Enceladus, a 50-kilogram magnetometer chemistry orbiter for Europa. Common mistake: payload bloat. Don't stuff a flagship into a fast bus. Pick questions that reward speed, transients, intercepts, time-critical events. There's also the mission architecture shift. Interstellar is a one-shot sprint followed by decades of coasting and an instant of science. Solar System class is iterative. You can pre-position relay nodes, test optical comms across U-scale distances, and validate diffractive patterns for passive beam riding. You can even practice braking without propellant. Solar photon pressure near perihelion or aero capture with thermal protection, because you can afford to try 5 times and lose 1. Let me show you exactly how intercept windows change thinking. With conventional propulsion, you plan years ahead. With a beamer, you plan months, sometimes weeks. The array schedule becomes like a launchpad manifest: targets, power slots, site weather, and orbital visibility. Adaptive optics and phasing software become your air traffic control. The payoff is agility. You can retask to a surprise interstellar visitor crossing the ecliptic or a fresh plume detected by JWST. Now you might be thinking, doesn't lower speed erase the advantage? Not if you're optimizing for science per year, not bragging rights. A fast Mars run in weeks cuts radiation dose, shrinks life support for future crew DMOS, and allows multiple shots at seasonal events. A Jupiter target in months means you catch storm evolution in real time. Even a trip to 70 AU for the sun's gravitational lens becomes practical within a career if you push harder on a heavier bus for longer. The belief break is simple. Interstellar ambition doesn't compete with local payoff. It enables it. The materials, metrology, optics, and autonomy you need for Alpha Centauri are overkill for Mars, which is exactly what you want when you're trying to ship hardware now. The reason this works is that the ground engine's cost dominates. Once you have it, each additional mission gets cheaper in both dollars and risk. Open loop for the next section. You've heard the claim, 3 weeks to Mars. Is that credible without hand-waving? We'll run the numbers, show sail-only versus laser thermal hybrids, and map the power, aperture, and payload sweet spots that bend the calendar. This is where abstract speed turns into a launch window you can circle on a calendar. The 3-week Mars window, numbers that bend time. Here's the claim on the table: weeks to Mars, not months. Bold is cheap, numbers are. So let's lay out 2 credible profiles you can actually engineer: a pure laser sail boost and a laser thermal hybrid, both using the same ground array we've been building toward. Why this matters: travel time sets radiation dose, life support mass for future crew DMOS and mission cadence. Cut time by 70–90%, and you change what science is possible and how often we can fly. First, say lonely. You start in medium Earth orbit so the probe sees the array for an hour-scale push. The thing most people miss is you don't need 0.2 C. Mars only demands tens of km/s above what rockets give you. Target a terminal speed of, say, 30–50 km/s relative to Earth. With a highly reflective sail and kilogram-class payload, that's reachable with a multi-megawatt per square meter spot sustained for tens of minutes, provided your aperture keeps the beam tight. You ramp power below structural modes, hold, then taper to avoid ringing. What does the trajectory look like? It's not a home and transfer. You're on a fast, tailored intercept. Depart when Earth. Mars geometry gives you a short chord. Aim for a direct flyby or quick capture assist if you bring braking. Cruise lasts 2 to 4 weeks depending on terminal velocity. Navigation is simpler than it sounds because the push is deterministic and ends near Earth. Deep space course correction is small. Now the hybrid, laser thermal. You carry a small tank of inert propellant, hydrogen, ammonia, even water, and run it through a beamed heat exchanger. The laser energy turns into thermal energy. Hot propellant exhaust produces high thrust with very high effective specific impulse compared to chemical. You use this for the first hour to stack delta V without brutal G loads on a heavier bus, then deploy a sail for continued low thrust or simply coast. The reason this shines is scaling. Laser thermal trades a little carried mass for a lot of thrust authority without needing the sail to survive the absolute highest flux. Numbers time in plain language. Suppose you want a 30-day Mars intercept. Average excess speed along the path needs to be on the order of tens of km/s above a standard transfer. A laser thermal stage with effective ISP in the thousands of seconds can add that in an hour-scale burn, assuming the array feeds hundreds of megawatts to gigawatts to the vehicle via beamed heating. Then the sail either tops up a few km/s over the next day while still in line of sight, or you accept the one and done and coast. Payload scaling lives here. For solar system missions, think 5–100 kilograms. At 520 kg, sail only with longer beam time is plausible if your aperture is huge and adaptive optics keep lock. At 2100 kg, laser thermal makes the math friendlier. You avoid 1000 G loads, you keep structural margins reasonable, and you still beat chemical transfer by a wide margin. The enabling architecture is the same for both. A kilometer-class phased array, exquisite phasing, and site selection that buys you dry, high, and stable air for adaptive optics. Common mistake: assuming you must either go featherweight or give up. The game changer nobody talks about is matching the mission to array duty cycle and aperture. You don't need the full interstellar beamer to make Mars fast. A smaller, earlier array with minutes of coherent lock can still deliver transformative gains when paired with a smart trajectory. Let me show you exactly how radiation exposure bends with time. Galactic cosmic rays don't care how fast you go, but solar particle events do. Shorter trips cut the integral dose and reduce the probability of catching a big storm mid-cruise. For robotic missions, that extends instrument life and relaxes shielding. For crew DMOS later, weeks instead of months reshapes the entire life support budget. What about the comms and guidance stack? With a fast trajectory, light time is still minutes, so autonomy is manageable. You pre-plan mid-course corrections and use optical navigation against Mars and background stars. The sail can double as a high-gain antenna after the burn. Diffractive patterns help here, so downlink rates improve during cruise and approach. Enabling infrastructure matters. Phased array sighting at high elevation deserts or islands minimizes turbulence. Adaptive optics and exo-atmospheric beacons stabilize the beam. You'll want grid-scale storage or dedicated generation for short, intense duty cycles. Thermal management on the array is a design in itself. Waste heat routing, active cooling, and beam quality monitoring to avoid speckle that would thump the sail. Okay, the what if that gets everyone excited. A rapid response mission to an interstellar visitor. The same stack that hits a 3-week Mars intercept can retask to a fast rendezvous with a newly discovered Oumuamua-class object. You don't wait years. You launch in days with a tailored push and a compact instrument suite. What do we finally see? Shape, spin state, outgassing chemistry. Answers we missed the first time because rockets were too slow. Limits and honesty check. 3 weeks is aggressive and assumes a sizable aperture, tight beam control, and a material stack that survives sustained flux without thermal creep. Laser thermal relaxes some constraints but adds propellant logistics and heat exchanger complexity. Best practice. Prototype with 520 kg DMOS to Mars or the Moon's far side. Validate beam riding and comms, then scale payload and power together. If you remember nothing else, remember this. The same beamer that dreams of Alpha Centauri can make Mars a fast neighborhood errand. Speed is a knob, and when you turn it with numbers, weeks become plausible. Building a planet-scale laser, phased arrays, and atmospheric war. We've talked sails and missions. Now we need the engine. Not a single Death Star laser, but a synthetic aperture made of millions of modest emitters acting as one. That's a phased array. Why it matters? Aperture sets diffraction, diffraction sets spot size, and spot size sets how long you can push. If you remember nothing else, remember this triangle: power, aperture, atmosphere. What is a phased array in plain English? It's a grid of laser tiles whose phases are timed, so their waves add in the direction you want and cancel where you don't. The payoff is beam forming and steering without moving parts. Nudge the phase map, and the far-field lobe slides across the sky in microseconds. Once you nail phase control, everything else clicks. You can put nearly all your power into a diffraction-limited spot millions of kilometers away, if the atmosphere behaves. Now here's where most people mess up. They imagine vacuum optics. We live under moving glass. Turbulence turns your perfect wavefront into a quilt of ripples that broaden and dance the beam. The reason telescopes use adaptive optics is the same reason our beamer must. You measure the phase the atmosphere imposes and pre-warp the outgoing wavefront so it arrives flat at altitude. The game changer nobody talks about is beaconing. Fire exo-atmospheric beacons. Read the distorted returns at many subapertures. Solve the phase screen in real time and drive deformable mirrors or tile phases to cancel it. Do that at kilohertz rates and stars stop twinkling for you. Site selection is propulsion here. Dry, high, and stable winds. The Atacama Plateau, Antarctic domes, high islands. Fewer water vapor cells, less turbulence, longer coherence time. Elevation buys you thinner air. Islands by laminar marine layers. Deserts by clear duty cycles. Common mistake, picking one site. A global network of arrays gives you weather resilience and longer line-of-sight arcs, especially for fast solar system pushes that want hour-scale burns from MEO. Let me show you exactly how the diffraction math drives size. The far-field spot width scales like wavelength divided by aperture. Have the wavelength or double the aperture, and your spot gets twice as tight. That extends your effective push distance before the beam spreads and your intensity falls. At near-infrared wavelengths where atmospheric windows exist, kilometer-class apertures make sense. Push to 10 kilometers and you're in the Starshot class. The cost and complexity scale, but so does performance. Thermal management is the unglamorous backbone. Even with efficient tiles, megawatts to gigawatts of waste heat must go somewhere. Tiles need micro-channel cooling, heat pipes, or liquid loops to reject heat without warping optics. Structures must stay dimensionally stable as temperatures swing. The reason this matters is beam quality. Thermal lensing inside gain media and air around optics creates phase errors that degrade coherence. So the array breathes. Active cooling, thermal baffling, and real-time beam quality sensors in the near field and far field. Phasing millions of emitters is a control problem, not a magic trick. You embed metrology, Heterodyne each tile against a master oscillator, distribute time with optical clocks and close loops on both phase and amplitude. Calibration never ends. Tiles age, some fail. The array detects drifts, reweights contributors, and routes around SIC modules. Swarm logic at the tile level keeps the macro beam healthy. That's the hidden win of modularity. Manufacturing yields don't have to be perfect if control can de-weight bad actors. Safety governance isn't optional. A beam that can push a spacecraft can blind instruments or heat debris. You build an air and space traffic integration layer that refuses to laze if any protected volume crosses the path. Predictive ephemerides for satellites, real-time radar and LiDAR keep the sky clear. International protocols matter. No unannounced firings, no pointing near populated air corridors, strict geofencing. The array must fail safe. Loss of lock or phasing faults drop power, not spray the sky with speckle. Failure modes are predictable. Phasing errors create side lobes, unwanted bright spots that waste power and potentially thump the sail. Speckle from surface roughness or coherence artifacts makes hot spots. Atmospheric anisoplanetism means the correction you apply for one line of sight doesn't fully fix another a few degrees away. Mitigation stack. Tiled subapertures with their own deformables, multi-conjugate adaptive optics to correct multiple turbulent layers, and real-time far-field cameras that see the spot on a cooperative reflector and drive corrections. You also dither the phase slightly to wash speckle, trading tiny intensity loss for big stability. Power architecture has to flex. The array doesn't run continuously, it sprints. That means coupling to grid-scale storage batteries, flywheels, thermal reservoirs that charge slowly and discharge fast. Duty cycles define economics. A beamer that supports solar system logistics can run daily at lower power. An interstellar shot is a few epic minutes. Either way, the plant's ROI comes from reuse. Upgrades roll in. Better tiles, shorter wavelength, smarter control. The engine gets faster while spacecraft get cheaper. Now the hard truth. Even with a perfect engine, the universe fights back. Beam ride is finite. Dust and air scatter steal photons. Clouds force pauses. That's why redundancy in sites and adaptive scheduling matter. You treat the beamer like an airport with weather delays. Manifest missions, retask when skies close, and use simulation to pre-compute power ramps that stay under the sail's thermal and mechanical envelopes. If you remember nothing else, remember this. The beamer isn't a single laser. It's a phased, adaptive, planet-scale optic waging war with the atmosphere. Build it right, and you own the most versatile propulsion engine humanity has ever had. Build it sloppy, and you get a blurry flashlight. Up next, even a perfect beam can't soften interstellar space. Dust, radiation, and decades of exposure demand designs that surviving relativistic space. Dust, radiation, and self-healing. Now the universe pushes back. At point 2C, a micron of dust isn't a speck, it's a bullet. The thing most people miss is that kinetic energy scales with velocity squared. Go relativistic and even hydrogen atoms pack MeV energies in your frame. Over decades, the leading edge of your craft becomes a sacrificial battleground unless you design for it. Why this matters? A single catastrophic hit can end a probe. Many small hits will sandblast it into failure. The benefit of mastering this is predictable lifetime. The consequence of skipping it is a mission that dies a silent death in year 7. The reason this gets tricky is you can't dodge what you can't see, and at point 2C you don't see much in time. So how do you live in this hail? First, geometry and materials. You narrow the frontal cross-section. You turn the payload into a needle behind a shield, not a slab. Think Whipple concept scaled down. A thin sacrificial bumper flashes the impactor into a plasma, a standoff gap lets the plume spread, and a denser back plate soaks the remaining energy. Metals with good thermal conductivity and low sputter yields. Think carefully chosen alloys. Make sense up front. Graphene or diamond-like carbon layers add strength to mass and resist erosion. The shortcut nobody teaches. Use layer density. Low Z materials up front reduce secondary radiation. Higher Z deeper layers arrest the cascade. Now add electromagnetics. Interstellar space is mostly neutral, but charged dust and ions exist. A forward coil or charged debris broom can deflect a fraction of charged particles before collision. You won't magnetically steer neutral grit, but you can shave the tail risk and reduce cumulative dose into electronics. If you can afford it, a tiny forward plasma sheath, created by a vaporized sacrificial film, can pre-ionize incoming micro-debris so fields bite harder. It's not a force field. It's a modest edge that compounds over billions of meters. Planning matters as much as armor. You don't fly blind. You choose trajectories through interstellar medium with lower dust density and you stack probability. Swarm redundancy is survival math. Launch hundreds, expect attrition, design the network to tolerate it. Common mistake, assuming no failures across decades. Design the mission so graceful loss is acceptable. Let redundancy do the heavy lifting. Radiation is the slow burn. Cosmic rays, solar events in the early outbound phase, and accumulated displacement damage degrade sensors and logic. Here, the shortcut. Self-healing and tolerant electronics. Some semiconductors can partially anneal radiation damage with targeted heating or laser pulses, localized annealing to restore lattice order. Metal halide perovskites have shown unusual recovery behaviors in radiation environments, and laser annealing in other materials can heal defects in situ. Pair that with wide bandgap devices for higher radiation tolerance, error-correcting memory, and watchdog redundancy at every layer. The reason this works is you accept bit flips and parametric drift as normal and designed for recovery, not perfection. Distributed architecture helps too. Don't put all brains in one die. Spread functions across chiplets with separate shielding compartments. If one module browns out after a hit, others reconfigure. The sail becomes a system part here as well. After acceleration, it can reshape into a comms reflector and also serve as a replaceable micrometeoroid screen ahead of the bus, slowly eroding while more critical hardware hides in its shadow. Let me show you exactly how HIT statistics guide design. You start with estimated interstellar dust flux along your path, integrate over area and time at your speed, and get an expected number of impacts above given sizes. Then you map each size bin to shield response, vaporization threshold, plume spread, residual fragment energy at the back plate. You size the Whipple gap and back plate thickness so that the 95th percentile impact won't breach, and you rely on swarm redundancy for the tail risk. If you remember nothing else, remember this. Armor the statistics, not the worst nightmare, then mitigate the tail. Navigation at speed is its own survival tool. You won't jink around individual grains, but you can avoid known clumps. Forward scouts in a staggered formation can sample the path microseconds to seconds ahead in your frame, radioing density spikes backward. At point 2C, reaction time is tight, but small attitude tweaks early can shed risk later. Even a few microradians of deflection integrated over light days moves you off a bad filament. Thermal spikes from impacts are another failure mode. A micron grain slams, a local hotspot blooms, conductivity saves you or it doesn't. That's why high thermal conductivity faces and heat spreaders matter. You couple the leading shield to radiators that face away from motion, and you design emissivity around the IR bands where you can dump heat without cooking your comms or optics. Software is part of survivability. You expect sensor degradation and calibration drift, so you build self-calibrating instruments that use stars and onboard references to re-zero. You expect intermittent brownouts, so you design state machines that resume gracefully, not brittle pipelines that crash. You expect partial memory corruption, so critical routines live in triplicated, checksum storage with regular scrub cycles. Micro-story. A lab team ran a decades in days radiation test on a candidate detector. Midway, dark current spiked and stayed. Old me would have called it dead. They pulsed a micro heater under the die for seconds, then scanned with a low-power laser. Defects annealed enough that performance returned within spec. They rewrote the flight plan, scheduled rejuvenation windows monthly, tied to periods of minimal science. The difference was accepting damage as a steady state and baking recovery into ops. Limits and honesty check. You can't armor your way past every grain. A head-on collision with a big particle is mission-ending for a single craft. That's why survivability is a stack. Smart pathing, thin front Whipple shields, thermal spreaders, electromagnetic shaving of charged flux, self-healing electronics, and swarm redundancy. Each layer cuts risk. Together they bend the odds enough that a fleet returns data. If you remember nothing else, remember this. At point 2C, survival isn't one technology, it's a strategy. Design the front to take the hits, the guts to heal, the software to forgive, and the mission to endure losses without failing. We'll need all of that because when we finally arrive, we can't slow down. So how do you do useful science when you can't break? That's next. Payloads that matter, from Starchips to science labs. We can push something fast, but what do we actually fly? Two classes unlock the mission space. Gram-scale Starchips for interstellar sprints and 2050-kilogram probes for rapid solar system science. Different masses, same engine, very different payload philosophy. Let's start with Starchips. The thing most people miss is that mass budgets in grams force you to rethink instruments from first principles. You don't miniaturize a DSLR. You build a camera on a chip. CMOS sensors the size of a fingernail with etched micro-optics can capture useful frames if exposure and pointing are pre-planned. Spectroscopy. On-chip gratings and photodiode arrays turn reflected starlight into a core spectrum. You won't get flagship resolution, but you can detect features like broad absorption bands, water vapor, maybe oxygen or methane, if geometry cooperates. Navigation and attitude live in MEMS. Gyros and accelerometers measured in milligrams give you inertial truth between star tracker updates. Star trackers, by the way, become coated apertures and tiny baffles bonded directly over the sensor. No moving parts. The reason this works is simplicity. At point 2C, there's no time for mechanisms to deploy, settle, and aim. Power is brutally scarce, so you scavenge during and after the push. During acceleration, tiny photovoltaic elements tuned to the drive wavelength can sip a fraction of the beam's side lobes or reflections for a brief energy harvest. Afterward, you trickle charge from starlight with high-efficiency thin film cells, then spend energy in short bursts for imaging and comms. Common mistake, planning steady loads. The right model is hibernation and spikes, with deep sleep most of the time. Comms is the hard problem everybody worries about, and rightly so. The light sail you used to accelerate can repurpose as a high-gain optical element. Diffractive patterns baked into the sail let you phase the outgoing laser or reflect a ground beacon with tight beam width. Data rates will be measured in bits per second, not megabits, so you compress ruthlessly and prioritize. Target images, spectra snippets, a few fields readings. Error-correcting codes stretch over months. You schedule long drizzle transmissions that add up to a packet. Autonomy must be ruthless and boring. A flyby at tens of thousands of kilometers per second gives you seconds near a target. You pre-program a sequence that arms instruments, triggers at star field cues, and throttles exposure dynamically. If you remember nothing else about Starchips, remember this. Every milligram and every millisecond must answer a single question. What's the one piece of data worth a 20-year wait? Now pivot to the solar system class where we get to breathe. At 2050 kilograms, you can carry mature sensors, high-resolution multispectral cameras, miniaturized mass spectrometers, radiation detectors, magnetometers, and even micropenetrators. The trade space opens up. You can put a small drill on a Mars quick lander or a sampling sniffer for Enceladus plumes. You can fly active LiDAR to map topography on approach and trigger a smart target cue. Here's the shortcut nobody teaches. Speed changes instrument strategy. Faster missions favor bursty, event-driven science. You don't tote a giant dish. You use the sail as a reconfigurable antenna for optical comms, and you ride the array's schedule to time your downlinks when geometry is best. You don't plan a sprawling payload. You select 2 or 3 instruments that can operate autonomously and survive high acceleration loads. Solid state, few moving parts, short integration times. Sail reconfiguration is a quiet superpower. After the burn, the sail can twist into a paraboloid-like reflector or a phased reflect array. That boosts link budget without adding mass. It can also act as a sunshade, thermal radiator, and sacrificial micrometeoroid shield during cruise. The reason this matters is multifunctionality. You turn the biggest structure you launched into 3 subsystems: propulsion, comms, and protection. Onboard intelligence scales with ambition. For interstellar flybys, autonomy is rule-based and clock-driven with minimal perception. For solar system sprints, you can afford more compute and real-time decision-making. A methane plume detected. Repoint the imaging slit, adjust exposure, and allocate more comms budget to that sequence. Seconds-long windows at Mars become minutes to hours at outer planets with sub-relativistic speeds. So a lightweight autonomy stack can prioritize scientifically rich frames on the fly. Trade discipline keeps you honest. Every gram added to structure or comm steals from the instrument you care about. Every milliwatt burned by a processor is a milliwatt you don't have for a spectrometer lamp. Best practice: start with the mission question, not the instrument wish list. Prove that each sensor produces a headline result independently. If 2 instruments answer the same question, pick the one that's lighter or more robust at high G. Micro story. A team obsessed over adding a micro wheel for fine pointing on a 15-kilogram Mars sprint. It cost 600 grams and failed vibe in testing. They scrapped it, leaned into fast exposures, and used the sail's diffractive trim tabs for course attitude. Net result: crisper images than the wheel prototype, higher reliability, and a simpler bus. The difference was accepting that speed favors simple optics plus smart timing over heavy stabilization. Limits and honesty check. Gram-class craft won't send postcards, they'll send clues. Kilogram-class sprints won't replace flagships. They'll scout, chase transients, and multiply shots on goal. That's the point. The beamer turns exploration into a cadence problem, and payloads that respect that cadence will deliver outsized science per dollar. If you remember nothing else, remember this: payloads that matter match the propulsion you have. Starchips ask one audacious question per gram. Solar system sprinters ask focused questions fast, with instruments that can take a shove, think for themselves, and phone home through a sail that became their antenna. Next up, we solve the whisper. How do you talk across 4 light years with milliwatts? Talking across the dark, interstellar communication hacks. We've got seconds of science at 0.2C, now we need years of whisper. The thing most people miss is that interstellar comms is a link budget problem first, not a sci-fi antenna problem. You win by stacking quiet, gain, and time. Start with the biggest thing you launched, the sail. After acceleration, it's dead weight unless you repurpose it. Here, that's the shortcut nobody teaches. A light sail can become a phased reflect array. Pattern it with subwavelength gratings and it doesn't just reflect, it shapes phase. That lets you form a tight downlink beam or coherently blink a passing beacon. Reflective gain scales with area. Even gram-class probes carry square-meter sails. Turn that into aperture, and your effective antenna jumps orders of magnitude without adding mass. How do you actually talk? 2 paths. 1. Onboard laser. You run a milliwatt to watt class diode, collimate through the patterned sail, and aim a microradian beam at Earth. 2. Beacon reflection. Earth or a nearer relay illuminates the probe with a powerful, narrow laser. The sail modulates the reflected light by tiny phase shifts. Think optical Morse to imprint data on a bright carrier. The reason this works is link inversion. The heavy power and pointing live at home. The probe just rides the wave and encodes. Now receiver advantage. On Earth, You don't squint with backyard telescopes, you build monster pupils. Synchronized telescope arrays synthesize huge apertures to collect every photon. And if you want the ultimate hack, you use the sun as a gravitational lens. At tilde 550-100 AU, sunlight's curvature focuses distant signals by staggering factors. Align a relay there, and a photon-starved link becomes plausible. Alignment choreography is the tax. Your downlink must graze the solar limb precisely. Your relay must hold station on a hair-thin focal line, and solar corona noise must be modeled and subtracted. Hard? Yes. Impossible? No. Power discipline is survival. A gram-scale probe can't chat continuously. You store energy slowly, thin-film cells sipping starlight, and transmit in bursts when geometry is ideal. Duty cycle becomes your fuel. Years of trickle charge by minutes of laser time. That means your codec must stretch across light years. Forward error correction with deep interleaving turns random erasures into fixable patterns. You accept single-digit bits per second and make those bits count. Once you nail that, everything else clicks. Timing is data. The probe transmits on predicted schedules so receivers can stack photons coherently. Coherent integration over hours boosts SNR without asking the probe for more power. You phase-lock Earth arrays on a pilot tone the probe sends first, then decode the payload that rides on top. If you remember nothing else here, remember that time and coordination are your hidden amplifiers. Swarm time diversity is the next lever. Not one probe, hundreds. They don't all speak at once, they take turns. Early arrivals send coarse finds, later ones refine with targeted passes. You stack their trickle streams for redundancy. If one fails, the network shrugs. If two overlap at Earth by chance, you use interferometric tricks on their slightly different Doppler shifts to separate signals and recover both. What about pointing? At interstellar distances, a microradian miss is a solar system-wide error. That's why the Sales antenna is paired with attitude truth. Star trackers etched into the payload keep inertial knowledge. The Sales diffractive pattern produces tiny, controllable torques for trim. Before each burst, the probe does a calibration sweep. It nods the beam in a micro-pattern Earth expects. The receiver correlates the nod signature and hands back refined pointing via prediction for the next window. No back channel needed, just shared ephemerides. Let me show you exactly what a 1-watt success looks like. Imagine a 1W, 1 microradian beam leaving Proxima's neighborhood. At Earth, a multimeter to kilometer-class optical array stares at the predicted patch of sky, narrowband filters slash background, and hours of coherent integration lock onto the carrier. Data arrives at a few bits per second. Over months, you accumulate a compressed image set, a handful of spectra segments, and key fields measurements. Not a live stream, but enough to answer headline questions. Is there an atmosphere? What molecules dominate? What's the magnetic environment like? Error sources aren't glamorous, but they're mission makers. Relativistic Doppler shifts move your carrier frequency. Dispersion and scintillation through interstellar plasma add phase noise. Earth atmosphere adds its own twinkle. Mitigation stack. Pre-compensate frequency using precise velocity estimates. Use adaptive optics and fast tip-tilt mirrors on the receive side, and spread spectrum modulation that survives phase scrambles. You design as if the channel is hostile because it is. Network thinking closes the loop. Earth isn't your only ear. Moon-based receivers dodge some atmospheric headaches. Deep space relays at Lagrange points extend contact windows. A future solar gravitational lens relay at 650 plus AU becomes the deep space ear for the hardest links. Each ear shares timing and partial decodes, and ground processing fuses them into a coherent stream. Common mistake, promising high data rates. Honesty wins trust. Expect bits, not kilobits. Compress like your life depends on it, because the mission does. Wavelet-based image compression with aggressive region of interest masks, prioritized packet queues, and onboard classifiers that only transmit interesting frames. The probe should throw away most of what it sees and send the gold. Microstory. A lab team tested a sail segment as a reflector ray, writing a simple phase pattern into silicon nitride. They shined a weak laser, modulated phase by microwatts of heat or power, and steered a milliradian beam cleanly. When they dithered a known PRBS code at a few kilohertz, the far-field photodiode recovered the stream with margin. It wasn't interstellar, but it proved the control path: phase, steer, encode. If you remember nothing else, remember this: area is gain, time is gain, and home field power is gain. Turn the sail into an antenna, turn Earth into a giant ear, and turn years into your ally. Physics says the whisper can cross the dark. Our job is to make relativistic reality count: time, frames, and human meaning. We've solved propulsion, survival, and the whisper home. Now the quiet truth. At point 2C, physics starts to bend how we experience the mission. Not sci-fi warp, just honest relativity showing up in the margins where plans either hold or drift. Why this matters: expectations shape funding and patience. The thing most people miss is that relativity here is modest but consequential. At 20% light speed, time dilation is only a few percent. The probe's clock runs a bit slow relative to Earth. Over 20 years of flight time in our frame, the onboard clock shaves months, not years. In practice, that means schedule margins, thermal cycles, and component aging all live on two slightly different calendars. If you don't plan for that, you'll misalign operations and deciphering windows. What does frames mean in plain English? There's the Earth frame, where we're watching a dot crawl for decades. There's the probe frame, where the journey feels a bit shorter, and the interstellar medium's particles look much more energetic. The reason this clicks is velocity defines what now means across distance. There's no single universal clock to coordinate everything. You build predictions that reconcile both frames and accept a little drift. Relativity also shows up in signals. We've already accounted for Doppler shifts and dispersion, but it's worth stating: the faster you go, the more your outbound transmissions slide in frequency and stretch in time for Earth. Planning isn't just about power. It's about where the energy lands in our receivers and how long we integrate to beat noise. Once you nail that, everything else clicks. Time dilation becomes an engineering parameter: small, predictable, budgeted. Now you might be thinking, if the relativistic effects are modest, why dwell on them? Because expectations kill projects more often than physics. Longer missions demand a different kind of audience. The Netflix analogy holds. A series that pays off over seasons needs open loops seeded early and reasons to stay. Interstellar exploration is the ultimate slow burn. You need institutional patience, a chain of nearer wins, and a culture that celebrates incremental payoffs. Mars in weeks, Pluto in months, the Solar Focus mission to 550 plus AU, while the Starshot coasts. Here's the shortcut nobody teaches. Design the narrative like you design the mission. Open loops at multiple timescales. Annual, lab milestones, metasurface efficiency jumps, adaptive optics field tests, reflector array comms DMOS. 5-year, solar system sprints that publish real data. Decadal, outer solar system and gravitational lens relays that prove deep space comms. Intergenerational, Alpha Centauri. A public that sees each loop closing keeps showing up for the next one. Ethics thread this too. Moving at speed through other systems raises contamination questions. Even flybys carry responsibility. We don't want our hardware to crash eons later into a world with prebiotic chemistry. In our backyard, rapid cadence means more objects visited, more chances to intersect protected environments. The right frame is restraint by design, sterilization protocols, safe trajectories, and targeting that avoids impacting potentially habitable bodies. We're not just fast, we're careful. Signaling is another quiet question. A laser array that can push sails can also ride in light across the sky. Do we use it to shout? Or do we keep it as a strictly local engine? The safe answer today: propulsion first, experiments later, governance always. Safety protocols for beams, international oversight, and clear norms about illumination beyond near-Earth space are part of the build, not a bolt-on. There's also the identity shift. For a century, our self-image has been rocket people, big tanks, bigger flames. Externalized energy and photon momentum feel alien at first. Delicate films instead of engines, optics instead of turbomachinery. But the deeper pattern is the same one that built the internet and the grid, central infrastructure enabling cheap, smart edges. The beamer is terrestrial cloud. The probes are clients. Once that clicks culturally, the economics and politics get easier to sell. Micro story, a grad student asked, "Why invest in a mission I'll never see finish?" The Pi pointed at the wall where the lab's first interferometer trace was framed. "You will. You'll see this line get steeper each year. Less noise, more signal. You'll see Mars in weeks. You'll see the lens relay light up. And when the star data arrives, maybe you'll be the senior scientist reading it with your students." The room got quiet. The difference was reframing Payoff from a single day in 20 years to a ladder of wins starting now. Limits and honesty check. Time dilation won't save you from dust. It won't magically compress 4 light years. Communications will still be photon-starved, but relativity gives you just enough wiggle room to be interesting without rewriting the mission. It's a spice, not the meal. If you remember nothing else, remember this. Long missions thrive when physics, engineering, and story align. Relativity nudges the clocks, cadence keeps attention, ethics steadies the hand. We're not just building fast probes, we're building a patient civilization willing to wait for the right answers while harvesting near-term wins. Next, we'll turn that into a playbook you can act on. Implementation playbook, from idea to launch. All right, let's turn ambition into a build plan you can actually run. 3 phases, each with concrete wins that stack. Material validation, ground array prototypes, and solar system demos. If you remember nothing else in this playbook, remember this. Reduce unknowns in the lab, retire risks on Earth, then prove capability in space with missions that matter. Phase 1, material validation. Your goal is simple: survive the beam without lying to yourself. Start with high-stress silicon nitride membranes, then layer in simple, one-dimensional metagratings where we've got strong evidence of passive beam riding stability. Why this first? It addresses the vaporization limit and stability in the same test. Build the microscopic trampoline variants, 4,200 micron squares, 5,100 nanometer thickness, released on tethers. Measure optical constants with ellipsometry, map roughness by AFM, and characterize emissivity in the mid-Earth. Then hit samples with progressively higher irradiance in vacuum while reading picometer motion by interferometry. The thing most people miss is process control. Swap one lithography solvent and your absorption tail changes. Like a clean flow, log every variable, and publish a material spec that others can replicate. Now fold in durability. You run thermal cycling at mission-relevant wavelengths, not just white light soak. You add pulsed power to emulate beamer noise and watch for resonance amplification. You do micro-impact testing with dust analogs at high velocities, followed by optical remeasurements, to quantify damage growth under realistic insult. Once you nail repeatability across labs, everything else clicks. You can scale features and be confident the physics scales with them. Phase 2, ground array prototypes. Start small and smart. A tiled meter-class subarray proves phase control, beam steering, and adaptive optics in the same breath. Put it on a dry, high site with access to infrastructure. Use an exo-atmospheric beacon, small satellite or retroreflector, to measure the phase screen and close the loop. The shortcut nobody teaches is to treat the prototype like a mission. Operations center, safety governance, sky traffic integration, and real-time beam quality telemetry. That's how you debug the system you'll scale later. Control architecture is your backbone. Heterodyne each tile against an optical master for phase locking. Run multi-conjugate adaptive optics with fast deformables to cancel several turbulent layers, not just one. Inject a small, known dither into the outgoing phase to wash speckle, and to create a calibration tone the far-field sensor can lock onto. Common mistake: chasing perfect coherence at the expense of robustness. You want a beam that stays useful when a tile dies, a mirror warms, or the wind shifts. Parallel track, safety, and policy. Before you scale, build the rulebook you'll live under. No laze zones, satellite deconfliction, automated cutoffs on ephemeris violation, and public dashboards for transparency. Persuading regulators is easier when you show them a prototype that already behaves like a good citizen. Invite international partners early. A global beamer is safer, more effective, and easier to fund than a national one. Phase 3, Solar System DMOS. You don't jump to Mars with an unproven stack. You run a ladder of missions that each retire a key risk and deliver real science. Quick wins first. A laser-nudged CubeSat in high Earth orbit that demonstrates beam handoff, passive beam riding with a simple grating sail, and post-burn sail reconfiguration for optical comms. Follow with a lunar far side relay. Beam a 510 kilogram probe to cislunar space in hours, flip the sail into a reflector, and push a high SNR downlink through the optical network. Then step to a Mars sprint demo in the 520 kilogram class. Validate thermal envelopes, G-survivable avionics, and optical navigation on a 2 to 4 week cruise. Avoid these traps along the way. Production before physics. Don't lock a factory while your material spec still moves. Payload bloat. If an instrument doesn't earn its mass by answering a specific time-critical question, cut it. Communications fantasy. Design your downlink around bits per second you can prove with a sail as antenna test, not around a dream modem. The reason this matters is reputation. Credible wins compound funding. Failed promises don't. Credibility moments belong in your plan. Cross-niche testing. Put your sail materials under third-party metrology at multiple institutions. Bridge lab to field. Run the same diffractive pattern on a microscope membrane and on a sub-meter outdoor sail with matching models, and show the same restoring torque behavior. Build a policy coalition. Astronomy, aviation, defense, and space agencies at the same table with a shared safety protocol. Once you show that coalition, the laser death ray narrative evaporates. Future pacing for the channel matters too. Viewers and stakeholders need the next rung. Promise and deliver, a diffractive sail stability deep dive, an adaptive optics live demo, a beam to sail thermal test, a rapid response comet intercept concept brief, and the teaser everyone wants, the braking paradox, how to stop at Proxima without fuel. Seed those open loops now, then close them one by one. If you remember nothing else, remember this cadence. Measure right arrow control right arrow demo. Materials that live, a beamer that points, missions that ship. That's how you go from a nanomembrane in a vacuum chamber to a probe whispering from 4 light years away. Concrete next steps. Here's your action list. First, map your mental model. Externalized energy versus onboard fuel. If that clicks, the rest of this series will feel obvious. Next, pick a rabbit hole and go deep. Metasurface design for passive stability, perovskite or laser annealing strategies for radiation-tolerant electronics, or MEMS payload stacks that survive high G, then draft a 3-week Mars mission outline. Sail only versus laser thermal hybrid, payload mass, comms budget, and the 2 failure points you fear most. Finally, line up your next watch, our breaking episode, how to stop at Proxima without propellant using stellar photon surfing and diffractive tricks. Bring your questions, I'll pull the best into the build plan. The takeaway is simple, we're not rocket prisoners anymore. Photon sails plus a reusable Earth engine turn speed into a software setting. Your challenge, choose one constraint, materials, beam control, survival, or comms, and design a test you could actually ship this year, even if it's benchtop. Post it in the comments so others can iterate. If you want the hard part next, how to break at Alpha Centauri without fuel, watch the Breaking Paradox episode queued here. And if you want the engineering deep dive, hit subscribe so you don't miss the diffractive sails and stellar braking series. Reminders before you click away. We still owe you the vaporization limit test, the real math behind 3 weeks to Mars, and the dust at 2C survivability stack. Plus the 1-watt home call, how a sail becomes an antenna. Next up, how to stop at Alpha Centauri without fuel. Vote in the comments, Mars in weeks or Proxima in decades, which ships first. Thumbnail ideas you'll see, 20% light speed. Laser SAILS, 3 weeks to Mars, ROCKETS are wrong. Check the description for links, Breakthrough Starshot, silicon nitride metasurfaces, and interstellar comms. Keep watching. The Breaking Paradox episode is queued right now.